everyone. I am Madhvi Gaur, Assistant Professor ABES Engineering College. Today I am going to discuss about binary search tree. What is binary search tree and what type of operations which can be performed on binary search tree? These will be the contents which I am going to deliver in today's lecture. That will be insertion in binary search tree as well as how we can search a particular node or a data item in a binary search tree. Let us start with binary search tree. As per the definition, it is a binary tree is called a binary search tree if each node n of that tree has the following property. And the property is the value at node n is greater than every value in the left subtree of n, and that value is less than every value in the right subtree of n. What we mean by this definition? Let us understand this definition with the help of an example. Consider a binary like this. Let us assume there is a node which has the value as 24. Then this value should be greater than its left child. And this value should be less than its right child. It means after 24, all those data items which are less than 24, that will be at the left side. And all those data items which are greater than 24, that will be placed at the right end. Let us understand this. Let us assume 24. Let us assume next data item is 13. And 13 is to be compared with this 24. And 13 is less than 24. That's why 13 will go or will be placed as a left child. Next data item, if I assume it as 28, then this value again needs to be compared with 24 and it will automatically go at the right side and it will be placed at a right child. Let us assume again next data item which comes into the picture is 17. Then that data item again needs to be compared with this 24. It means we have to every time compare the value which is to be coming into the future, that is to be compared with the root value. First, we will do the comparison with the root node, and then with its further child. Let us assume the next data item is 17. Then 17 needs to be compared with 24. Then it is less than 24. Then it will go to the left part. Then again there is placed some value which is 13 and it needs to be compared with 13. Then 17 is greater than 13. Then it will go at the right child or the right side. Let us assume the next data item is 21. 24 is greater than 21 and it means 21 is less than 24, then it will be go at the left side. Then we will compare 21 with this 13 which is greater, then we will go to the right side. Then we will compare 21 with this 17. 17 is less than, it means 21 is greater than this 17, then it will automatically go at the right side. Let us assume the next data item is 30. Then we have to again repeat this procedure. It will be compared with this value. 30 is greater, so we will move towards the right end. Then 28 is less than or 30 is greater than 28. Then it will again move to the right child. Then 30 will be placed here. And repeatedly until all the data items will be traversed, we need to do the insertion like this process. Okay, let us consider another example. We have to perform the insertion in a binary search tree, and these are the data items which needs to be inserted into the binary tree. We will assume the first data item as a root node. It will be our root node. The very first node will be considered as a root node. Then first we have to insert 40. The insertion will be like this only. After that, the next data item which needs to be inserted, that is 60. Then we have to compare 60 with this 40. 60 is greater than 40, then it will go to the right side and it will be placed as a right child of this 40. The next data item is 50. We need to again the compare 50 with this 40. But 50 is greater than this 40, then we have to move towards the right side. Again, we have to compare 50 with this 60. Then 60 is greater and 50 is less than this 60. Then we have to move towards left side, which will be placed here as a left child. Next data item is 30. We will compare 33 with this 40, which is less than 40. So it needs to be placed here. Next data item is 55. 55 needs to be compared with 40, which is greater. So we will move towards right hand side. Again, 55 needs to be compared with this 60. Then we have to move towards left side. Then we will compare 55 with this 50, which is greater than this 50. Though, so we will move towards right side. Next data item is 11. We need to compare with this 40, which is less than. We will compare with 33, which is less than. So we will move towards left side. So this is the final binary search tree corresponding to all the data items which needs to be inserted one by one. And we have to repeat the procedure until all the data items will be traversed. It means we have to compare all the data items with the root value only. Okay, let us understand this concept through the algorithm. This is the algorithm which I have followed for creating or for inserting any data item into a binary search tree. Let us first understand how we can create a node into a binary search tree or into a simple binary tree. If I want to insert a new node which can be assumed as a parent node which do not have further child, it means the very first node we have to insert or create. Then at that time we have to refer this algorithm. Let us understand what are these steps explaining here. In the first step, initially, there is a syntax new node is equals to struct node pointer malloc size of struct node. What does it mean? This step is basically used for creating a node. And we are already seen in my previous lecture that how we will define a structure corresponding to a node. It means it will have info part, it will have left child, as well as it will have right child. Okay, here we are just dynamically creating a node, and for defining a node dynamically at runtime, this is the syntax corresponding to it. Then what is doing here? What we are doing here? We are assigning new node left is equals to null because we are just creating a single alone new node which do not have further child. That's why I have assigned new node left is equals to null. In the next step, I have assigned new node if info is equals to item. Let us assume the value given by item is 25. So we will assign new node info is equals to item, which is 25. And the name of this node is new node. This will be the left child, this will be the info part, and this will be the right child. Then new node right is equals to null. We will assign the new node right child is equals to null. Then we will return this new node. It means dynamically it is stored at a particular address. Let us assume this address is 2000, which is returned by this algorithm. So if I want to initially create a node, then this will be the procedure that which we have to follow, and it will return an address at the end. Now let us consider this insertion into a binary search tree algorithm. Initially, if I am thinking there is no node, then root address written by the algorithm will be definitely null because there is no such node. If we do not have any such node, then the address pointed by the root node will be null. It is not allocated any memory space. That's why it is returned as a null. Okay. Let us assume we have to insert few items. Let us assume 14, 28, 19, and 30. Let us perform the insertion corresponding to all these data items. Okay. Then we have to follow this procedure. Initially, there is no such root node. That's why initially the root node's value pointed by is none. Then we have to invoke the tree create node function. Then it will call this procedure, and we have already discussed this procedure. What this procedure is doing, we are initially creating a node in which we are assigning the value, and the left child will be assigned as null and the right child will be assigned as null. While concentrating on this example, let us consider with 14. Initially it will be drawn like this. It means it will be 14 here, and left child will be null and right child will also be null. Again, if I want to insert next new item, which is 28, okay, we will again call this procedure. Now, the value pointed by root will be this. Let us assume this address is 1000. The address returned by this algorithm of create node will be 1000, which will be used here. So, the value passed here is 1000 and item value will be 14. 14 we have inserted already. So next value will be 28. We will compare this value if root is equals to null. No, because now root value has been updated as 1000. Then it will go to the else part. In the else part, we are comparing item, which is 18, is less than root info. And what is here? Root info is 14. Item is 18. Then this condition will not be executed here. It will go to the else part and it will assign root right is equals to tree insert. It is again recursively called the same procedure. It is again recursively called the same procedure in which we are passing the value as root right, which is null now, and item, which is 28. Because we have not connected these nodes, or even we have not created a block for the data item, which is 28. So first we have to create a node, then the interconnection will be done. So for the root info, the new value passed will be null, comma, 28. Because it is again recursively called the same procedure, but new passed value will be null and 28. Then the control will go here. Now root value is null and item value is 28. Root is equals to null, condition will be true. Then again it will invoke the create node function. What is the value returned by the create node? It will again allocate a memory block in which info part will be assigned the value info, which is 28. Left child will be termed as null, right child will be assigned as null. It will, at the end, it will return a value, which is address allocated by this, which is what? That is, let us assume 2000. Then the value returned here will be replaced here, because tree insert call this procedure which has returned some value invoked by this procedure. And the value return of the new block is 2000, which will be assigned here. It means root right, earlier root was this value, which is 1000. 1000 right, which was earlier null. Now it will be assigned a new value, which is replaced here, which is 2000, the address returned by the create node function or the procedure. So we will interconnect this node here. Because if we will follow the binary search tree concept, 28 is greater than 14. That's why automatically 28 will be placed as a right child. But if I execute this algorithm, you can see here, automatically the connection has been done with the right child of its earlier root. Yes? Okay. Now the next data item is 19. We will again call this procedure. Root value assigned again as 1000, because every time we have to focus only on 1000, which is the return value of the root node. Because here we are every time returning the value root address. Because in the last slide, I have already shown to you that every time if I want to insert a new value, every time the comparison needs to be done with root value. That's why for every time, whenever we are executing this algorithm, we are just returning the address of root, which is 1000 here. Okay. The next value is 1000, comma 19. The new function call will be 1000, comma 19. We will check root is equals to null. No. Then it will go here. Item, which is 19 now, is less than root info, which is 14. No condition will be false. Then again, it will go to the root right part and it will again invoke the same procedure. The new value passed here will be root right. What is the root right address here, which is 2000? Then it will invoke 2000, comma item, which is a new item, which is 19. Then this procedure will be invoked again, but for the new values, that will be 2000 and 19. We will again invoke this function. Here the value will be passed here 2019. Root is not null. Then again it will go here. 19 is less than root info. 19 is less than root info. Now root is 28. Yes, condition will be true now. Then it will invoke the tree insert function again. Why we are invoking this function again? Because we want to call create node function, which will allocate a memory block. Okay. Then it will allocate a block like this into the memory, in which the info part will be 19. Then left child will be null, right child will be null. And this value, the address written by here, which is 3000, will be assigned here. It means root left will be connected to 3000 now. And this is root left. This will be connected with this node now. Okay. And while applying the BST concept, we can again see 19 will be compared with 14, which is greater. Then 19 will be compared with 28. Then we will go to the left part and it will be placed here. For the 30, we will repeat the same procedure again and again. So the last final binary search tree will look like this. If we will just draw a binary tree, not the linked representation of it, then it will be like this: 40, then 28, after that 19, and then 30. This will be the final BST or the binary search tree corresponding to these data item which has been assumed by me. Okay, next. Next, if I want to search a particular item, then this procedure will examine the position of that node where it is present, as well as its parent index as well. Where the item is and want to know about the parent information as well. Then we have to follow this procedure. If root is equals to null, then it means if root is null, then then we cannot find out the data item which I am looking for. That's why the location will be null, as well as its parent location will also be null. And we will return this value. If root info is equals to the desired data item for which I am looking forward, then the location will be assigned as the root address and the parent location will be assigned its parent value, which will be the root parent. Okay, but we know root, there is no parent of root. That's why it will indirectly return the value as null. If first time we are looking for a data item, only then. If data item for which we are looking for, which is K, I am assumed here K, which is the data item. This PAR denotes the parent of that data item, for which I am looking forward, and it will point out the root address, which is the root data item inside a binary search tree. If data item is less than root info, then we know the procedure. Then we have to traverse the left part only. As in the previous slide, or I have already discussed, if the data item which is to be inserted is less than the required root data item, then we have to traverse the root left part. Okay, that's why I am assigning the parent value as root node. If the data item value is greater than the root info, then obviously we have to traverse the root right part. And accordingly, the parent node value will also be updated. Okay, we can also examine this with the help of any example. Let us assume a binary search tree 14, 13, 17, 21, and 16. One more data item, we can assume it as 11. We can verify as this. All the data items which are to the left to the binary search tree, it will be less than, should be less than this root node value. And all the data items which are present into the right hand side, that should be greater than this data item. Okay, let us consider I want to search for 16, whether this data item is present inside this binary search tree or not. Let us see. Initially, I'll assign all these data items as some address. Randomly, I'll assign the data address to these data items. Basically, the value returned by here will be in the terms of addresses, because we are just directly concentrating on the linked representation of all this binary search tree. Okay. Initially, I should have the root node address from where I have to look forward or to start the searching criteria. For this, I have used this tree search. Okay. Initially, I should know what is the address of the return, which will be returned by some of the algorithm. Let us assume insertion. Then it will return the address of the root node, which is 1000. I just assume or write down 1000 here. The data item I needs to be searched is 16. And initially the parent will be assigned as null, because we know there is no parent of the root node. That's why the value we assigned here will be null. Initially, I will compare with this value, root is equals to null. No. Root info, which is 14, is equals to k, which is 16. No. Root info is 14 first time, is equals to 16. No. Next time, 16, which is k value, is less than root info, which is 14. False. Then next part, obviously else part will be executed now, because these three condition has been false. Then we have to follow this procedure. In that case, parent will be assigned as root address, which is 1000 here. Then we have to recursively this procedure, in which we are calling root write. What is the address of root write? That is 3000. So new updated value here will be 3000, comma 10, which is a data item I am looking forward, and parent latest value is 1000. These value will again go or recursively call the same procedure. Again, we will compare with this value, because now the new values are 3000, 16, and 1000. Okay. Then root is equals to null? No. Root info, which is now root value is this. Okay. 3000. We have to look forward this only. Then root info, which is 17 for the second time. 17 is equals to 16. No. Then k, which is 16. 16 is less than root info, which is 17. Yes, condition will be true. Then the now parent updated value will be PAR will be assigned as root. PAR will be assigned as root, which is 3000 now, because we have assigned the value of root as 3000 here. Then PAR will be assigned as 3000. Okay, the latest value of the parent node, if that particular node meets here. Then we will again recursively call this procedure. Root left, this is root, which is 3000, which we have called here. 3000 left is 5000. The new value will be 5000, comma 16, for which we are looking forward, and parent will be now 3000. Again, we will call this procedure, and then the new value will be 5000, comma 16, and 3000. This will be false condition. Root info, root is 5000, which is this value. It means for the third case, it will be root info is 16 is equals to 16. Yes, condition here. Condition meets here. It means we have got our desired element. Then we will set the location as root. And what we have passed the value of root as 5000. It means the value returned by LOC is root, which is 5000. And parent of that location is PAR, which is 3000 here. It means we have got our element at the location or at the address which is pointed by 5000. It means we have got my element 16, which is present at the address 16, and the parent of this node is written by this value, which is 3000. It means we can, through this algorithm, while executing this algorithm, I can know the address of that location where I find out my element, as well as parent of that node as also. Okay, so we have find out the parent of that particular node that exists into this BST for which I am looking forward, as well as the address pointed by that. Okay, this is the reference which I have taken for preparing this lecture. In the next PPT or in the next video lecture, I'll discuss about deletion, which is the another binary search tree operation, as well as threaded binary tree and Huffman tree algorithm. Okay, thank you, and thank you for the patience listening.